All right, so welcome to the last talk of this session. We are going to have two speakers, and the first one will be Tanmay Singal. And he is going to tell us about the implementation of quantum measurements using classical resources and just one ancillary qubit. Over to you, Singal.
Thank you very much. Firstly, I would like to thank the organizers for giving me this opportunity, for giving us the opportunity to speak about our work. This work is done with me, Filip Maciejewski, and Michał Oszmaniec from the Center for Theoretical Physics, Polish Academy of Sciences. The title of this work is the implementation of quantum measurements using classical resources and only a single ancillary qubit. So let's get started. So now the outline of the presentation. First we'll set up the problem. The problem is that of the cost of implementing general quantum measurements. We will see that resources to implement these measurements can be divided into classical and quantum. Then we will present the scheme to implement the general quantum measurements using a single ancillary qubit with post-selection. And then we will talk about whether the scheme is good or bad. Filip will then take over to talk about numerical results that we have for the scheme. After Filip, I will take over to talk about analytic results for Haar random POVMs. Based on this evidence of the performance, we conjecture something, and then we give noise analysis, and finally we conclude. So let's continue. To extract information from a quantum system, you need to perform a measurement on it, which is a probabilistic event, and the probabilities for all these for the event outcomes are given by Born's rule. Now, quantum measurements find applications in various scenarios, such as communication, metrology, tomography, and computation. Right, so now let's dig a bit deeper into quantum measurements. The simplest kind of quantum measurements that you can perform on a system are known as projective measurements. Over here, you have some system whose some observable you perform a measurement upon, and you get measurement outcomes. So this can be described by a set of projector operators, that is positive semi-definite operators with some identity, and they have this orthogonality relation. More general quantum measurements are known as positive operator value measures, or POVMs, and they can be described using what is known as Naimarks dilation theorem. So what is going on over here? Well, you have some quantum state. You attach to this quantum state some fixed ancillary system, okay, so some ancillary system in a fixed state. And then you perform a global projective measurement on this combined system. This will end up implementing some measurement on your principal system. This can be described by a set of positive semi-definite linear operators, which are known as the effects of the measurement, which sum to the identity. Okay, now let's take this forward. Now, a generalization of Naimarks dilation theorem tells us that when our principal system is that of an n-qubit system, then to perform the most general quantum measurement on this n-qubit system, you need to attach at least n ancillary qubits to your principal system. Now, this poses a problem when you want to implement this most general quantum measurement on your system, because you will have to attach large number of ancillary qubits. The circuit width becomes larger, and hence the implementation becomes more noisy. Also, from the perspective of near-term quantum computers, there are issues like qubit connectivity, etc. Hence, you are motivated to find other ways, other strategies to implement the most general POVM with only a few quantum resources, that is, few ancillary qubits. Right. Now, what are the free resources? Well, let's assume that classical randomness is free. So when classical randomness is a free resource, then that frees up two operations. The first operation that I'm talking about is classical mixing. So what happens over here is that you can implement, let's say that you can implement POVMs M and K. Okay, so what you do is you implement this POVM M with some probability P, and then you implement K with some probability 1 minus P. Over many trials, what ends up happening is that you implement another POVM L, which is a probabilistic mixture of both of these POVMs. This is called classical mixture of M and K. So that's your first free operation when classical randomness is free. The next free operation is known as classical post-processing. What happens over here is that you have some POVM M, you implement it and get outcomes, okay? And then you perform some coarse graining over all of these outcomes. So over the course of many trials, the statistics that you get after this coarse graining will correspond to the implementation of another POVM, which is denoted over here by calligraphic Q of M. So this calligraphic Q is, this is the operation of classical post-processing. So this is your second free operation. Okay. Now I will introduce another operation, and this operation is not free. Okay, in contrast to the earlier two operations. So over here you have some POVM L, and let's suppose that there is a scenario where you are only interested in a subset of the outcomes of L. And let's denote those outcomes by I, and let's denote the remaining outcomes by J for junk, for instance. So you implement L, and then you post-select on the outcomes that you sample only from the outcomes that are desirable, and then you discard the remaining. This operation is known as post-selection. Now, in special circumstances, you can implement a POVM M by post-selecting on the outcomes of L. So what are those circumstances? Well, when L is a probabilistic mixture of a POVM M and another POVM in such a way that some subset of outcomes correspond to M with this probability, and the remaining outcomes correspond to, let's say, they're junk outcomes, you don't care about them. In that scenario, when you implement L, and then you post-select on the outcomes of M and discard the remaining outcomes, then you can implement M via this post-selection method. So the success probability of implementing M, of simulating M, that is given by this Q success factor. So this is the third operation that I'm talking about. So over here, the cost of implementation is this it's this 1 minus Q success. Okay, so these are the three operations. Now, using these three operations, let's get to a scheme to implement an arbitrary POVM M. So a POVM M using only a single ancillary qubit and these these POVM operations. So your target POVM is some POVM M. So these are the effects, and let's say that the rank of these effects is equal to 1. The number of effects that you have, the number of outcomes that you have is this little n. So let's start the scheme. First step. So take the numbers 1 to 3 up to n. Choose some partitioning of this set of numbers such that each subset of the partition that you see x1, x2, so on and so forth is of size little m. Okay. Now, corresponding to each of these x1, x2, these subsets, you find some POVM n subscript x subscript 1, so on and so forth. Now, these n's, these POVM n's, they are such that they can be implemented using only a single ancillary qubit. Okay, we will learn more about them on the next slide. Okay, what they are, where they come from, how they can be constructed, etc., etc. That will come on the next slide. Let's just suppose that you have these POVMs. Now let's get on with the scheme. So I will talk about the scheme in sort of a schematic fashion without giving the details of how it actually works. So what's going on over here? So over here on the right-hand side of, on the left-hand side of this equality, you have your scheme. Okay, so what's happening over here? Well, there is some probability with which you randomize over the implementation of these n's. Okay, so you perform them in this randomized fashion, and then you strategically perform some post-selection operation and some, post-processing operation and then some post-selection. This entire scheme, which I just mentioned briefly, it's done in a strategic manner that this scenario that you see on the right over here, that is what's going on. So what's going on over here is that you end up implementing a POVM that you saw L, such that some subset of its outcomes correspond to the target POVM M, and the success probability over here is Q success. So when you post-select on these outcomes, then you will end up implementing your target POVM M with this success probability Q success. Okay, now let's come to these n's that I talked about in the previous slide. How do you construct them? So as I mentioned on the previous slide, you're supposed to start with a partitioning of the numbers 1 to n. Now let's choose a standard partition. Okay, so let's say that like the first subset comprises of the numbers 1 to m, then the second subset is m, second subset is m plus 1 to 2m, so on and so forth. Collect the effects which correspond to the indices occurring in the first subset, and then collect them into a POVM. Of course, you will have to add another POVM effect so that all these guys over here, they sum to the identity. So do that for the first set, do that for the second set, and construct another POVM, so on and so forth. Okay, right. So this is how you construct these n POVMs, these POVMs big N. Now you may wonder, where have we put in the information that these POVMs are implementing using a single ancillary qubit? Well, we said that the effects M, they are rank 1. Okay. Now, when you combine that with this constraint that this little m has to be less than equal to d, then that will ensure that these POVMs n subscript x subscript j, they are implementable using a single ancillary qubit. Now let's come to the success probability. So the success probability that I mentioned on the previous slide, it has this form where you have an outer summation and an inner summation over here. So the outer summation is a summation over the different subsets in your partition, and in the inner summation you're summing over the effects which occur corresponding to some subset of your partition, and of course you're taking the reciprocal over here. So this is your Q success. Now let's look a bit more closely to this at this Q success. Your Q success is actually a function of the partitioning that you choose. So different choices of partitioning will give you different values of Q success. Okay. Now, hence it follows that the maximum value of Q success will be obtained when you maximize over all possible partitions. Right. Now, what is the physical interpretation of this Q success? Well, it is the reciprocal of this Q success is the average number of times that you need to implement this scheme so that you can sample once from your target POVM. Okay, this means that this Q success is the figure of merit of your scheme. Okay, okay. Finally, also, I'll just mention briefly over here, and we'll see this again later for a while, that this Q success is actually related to other properties of this POVM, which are related to resource theories. Fine. So now we have presented the scheme. We've talked about the success probability. Is this scheme good or is it bad? To do that, let us compare this scheme with an earlier scheme. Now, this earlier scheme was given by my collaborators, Michał, Oszmaniec, and Filip Maciejewski, and their collaborator, whose name I find a bit difficult to pronounce.
Zbyszek Puchała.
Yeah, thanks, Filip. Right. Yeah, so what happens over there is that you simulate an arbit. So the scheme is very similar. It works by simulating, it simulates arbitrary POVM with classical resources, but using no ancillary qubits. Now, contrastingly, in our scheme, you use a single ancillary qubit, but in that scheme, you don't use a single ancillary qubit. In that case, they find that the worst case success probability scales as 1 over d, where d is the dimension. Now, this is not good for large values of d because the scheme becomes infeasible, right? How does our scheme compare how is our scheme in comparison? Well, the scaling of the success probability is significantly better, and we actually expect that the Q success is above a constant for all POVMs in all dimensions, and there is actually strong evidence for this in this work in the form of numerical results and analytic results. So now I hand the floor over to Filip, who will be talking about these numerical results. So Filip, the floor should be yours.
Sorry, can you hear me now? Hello?
I can hear you.
Ah, okay, super. Sorry, I got some problems with my mouse. Okay, hello everyone. I'm Filip, and I'm here to provide you with a short interlude in Tanmay's presentation, and I'm going to tell you how designing the implementation of quantum measurements via our protocol works in practice. All right, so we heard from Tanmay that the figure of merit here is the success probability of the implementation, so like the average fraction of a time that we sample from the target probability distribution. And this can be expressed in terms of a norm of the measurement operators, which are divided into some subsets denoted by xj, right? Well, the problem here is, as Tanmay mentioned, that, well, there is really a lot of possible partitionings of measurement outcomes, and in principle, this could turn out to be very hard to find a good partitioning, okay? And well, to investigate that, we did some numerical experiments, which I will now describe. So we tested it for 3 classes of measurements of rank 1 POVMs with d-square outcomes. Okay, so to focus attention, you should now think about measurements in dimension d, which have d-square outcomes. The first class was Haar random POVMs, and to understand what I mean by that, let me first explain how unitary in dimension d-square defines a quantum measurement. Okay, so we have this d square by d square unitary matrix, and we can look at the first zeros of this matrix as d-dimensional vectors. So the number of those vectors is d square, and each such vector can be used to define a measurement operator via outer product. And since this matrix is unitary, it actually follows that a set of such operators form a proper POVM. And finally, now Haar random POVM is simply a POVM defined by a unitary, which was drawn randomly from Haar measure, a uniform measure on the unitary group. Okay? Right. The second class of measurements we investigated are informationally complete measurements covariant with respect to ZD times ZD group. So this name have two important parts. The first part, informationally complete, simply means that the measurement operators span the space of operators on our Hilbert space. Okay. And now the second part, that the measurement is covariant with respect to some group, means the following. So such measurement is defined by a single fiduciary vector psi0. And now the other vectors are related to this psi0 via the unitary action of the group, which in our case is this ZD times ZD. The set of those vectors, which size is the size of the group, defines a quantum measurement via the outer product. And here is proportionality means that there should be also some number. Finally, the third class is closely related to the second one. Basically, we just add symmetric at the beginning of the name. And for the purpose of this presentation, you can think that those are the same measurement as in the second class, but with additional requirement that the overlaps between measurement operators must be equal, okay, for all products. Right, so those are the three classes of measurements that we tested numerically. I suspect that most of you might be familiar with like generation of random unitary matrices, which define then random measurements, but you may reasonably ask whether it is clear how to construct those two other classes of measurements. So in the case of second class, there actually exists an explicit simple construction in this work. If it comes to SIC-POVMs, well, it is actually an open problem to construct those in arbitrary dimensions. So it is like an area of active research to find those symmetric informationally complete POVMs. Currently, a bunch of them has been found numerically, and there are even databases where you can find some of them. We actually had a good luck here because Markus Grassl shared with us a lot of high-dimensional SIC-POVMs, which are not currently available on the internet. So thanks a lot, Markus, for that. Right, so let's go to the numerical results. What we actually did, well, the first step of the numerics is, of course, to construct a measurement of interest, which belongs to one of those three classes I mentioned. Now, the second part is to test a preferably small number of partitioning of measurement outcomes, calculate those norms, and choose the one which gives the best success probability for our protocol, okay? And in our case, this number of partitioning is really small because it's up to like 24 across the tested dimensions. And the last information we need is, of course, the size of the subsets of the letter M from Tanmay's presentation. And here we set it to be equal to the dimension of the Hilbert space. This is precisely the case which allows to implement the measurements using only single ancillary qubit, which was promised in the title of our talk. Okay, so what I will present to you now is a graph in which y-axis will be the success probability and x-axis will be the dimension of the Hilbert space. So the range of dimensions is like this. For random, it's up to 1000, and for SIC-POVMs, it's over 2000. So it might sound like not so big number, but you must remember that the number of outcomes here is like d squared. So it quickly becomes computationally intensive to calculate all of this. Okay, so here's a graph for random and SIC-POVMs. You can see the colors. And how it looks, well, you can probably observe that it actually seems that the success probability somehow does not want to go to 0, but rather to some constant. And if I draw a line here, it actually looks like it's going to 25%, which is quite nice. Of course, this plot is quite hard to inspect by eye, so we can change a little bit what we are plotting. So now I will subtract from the success probability the 25%, which might be this constant that it's going to, and plot everything in the log-log scale. Okay, so if you're not familiar with this method of data analysis, it's like quite handy in searching for some power laws in the functional dependencies. So basically, if what we will see is a straight line, it might indicate that the non-constant part, this part depending on the dimension of success probability, decays with some power law with the dimension, meaning that the whole success probability actually goes to a constant. Okay, so this is the plot in log-log scale. So it looks like this is a straight line, right? A lot like it. So those results indicate that for random and SIC-POVMs, the success probability of our scheme actually goes to 25% with the growing dimension. So of course, this is just a numerical indicator. It cannot be taken as a definite proof. So what happens if we do the same for the informationally complete measurements, but which are not symmetric? Well, here at first glance, we have a similar behavior. Okay, now with a lower constant, which seems to be going to like 19%. But now, if I plot the same stuff in the log-log scale, it doesn't look so much as a straight line anymore. So this might mean that eventually this success probability actually goes below the 19%. And so for those informationally complete but non-symmetric POVMs, the results are not that clear. But like even if the success probability decays, it is very slow decay. Okay, so it might be some other lower constant that it goes to. Right. Okay. So this was the part about the numerical results. So let me summarize. First observation is that it is very easy to find good partitions for tested measurements. Okay, I only needed a few of them to get a good success probability. And about the question whether this probability is above a constant, well, for non-symmetric informationally complete POVMs, it is not so clear for those results. But SIC and Haar random POVMs seem to be above 25%, which is quite good. Okay, and now Tanmay will actually explain to you why for Haar random POVMs those results are not so surprising. Okay, so Tanmay, go ahead with the next part. Thanks.
Hello, thanks, Philip. Right, so now I will present analytic results for Haar random POVMs. As Philip mentioned, the number of outcomes of your target POVM is d squared, and m is equal to d. So what we do is we fix the partition of the set of numbers 1 to d squared. Okay, let's choose a standard partition x1 goes from 1 to d, so on and so forth. Okay, so this partition is fixed. Okay, now we saw from Philip's slides how this POVM M was constructed from a unitary U. So this is a d squared by d squared unitary. If you remember Philip's slides there, he used symbol V. Right? Now the success probability is a function of this M, and M is a function of U. Hence, the success probability is actually a function of this d squared by d squared unitary U. When you equip the unitary group with the Haar probability measure, this converts this Q success into a random variable. Okay. Now, given that it's a random variable, you can study its properties like its average, concentration, etc., etc. Okay. So this allows us to do that, and that is precisely what we do over here. And I will explain what is going on over here in the next slide. But before I do that, I would like to mention that, look, so what we have done over here is we've given a simplified version of the result for n is equal to d squared and m is equal to d. But we actually also have more general results for general n and general m. Now let's come to this result for Haar random POVM. So what is going on over here? Well, you see on your screen an inequality where on the left-hand side you have the probability of a certain event, and then this is upper bounded by some guy on the right-hand side. So what is this event? Okay, so over here you have the unitary group, and this is partitioned into two sets. The green set corresponds to Q success being greater than 6.5%, and the red set corresponds to Q success being less than 6.5%. It is the red set whose event is shown in this inequality. Okay, so what happens when the dimension increases? Well, as dimension increases, you can see that this is what is taking place. And I mean, so this red set, the probability of this red set, this starts to shrink. And how does it shrink? Well, it scales, the shrinking scales as this. Okay, so this is the result. Basically, it tells you that with overwhelming probability, you can expect that Q success will be greater than 6.5% for large but finite dimensions. Okay, so based on these results, the numerics as well as analytic results, we formulate a conjecture that any target POVM M can be simulated using our scheme with success probability, which is above a constant. And this is independent of like what our choice of POVM is, and this is true for all dimensions. That is, the Q success will be greater than C for POVMs in all dimensions. Okay. Now, what are the consequences if this conjecture is true? Well, firstly, implementing this scheme for higher dimensions is feasible. So you can implement your target POVM using only a single auxiliary qubit. But there are certain other consequences which come from a resource theoretic perspective. Firstly, for quantum state discrimination, it says that you don't need too big an auxiliary system to perform well, to discriminate your quantum states well. And also this has consequences for robustness of randomness extraction. Finally, I'll come to noise analysis. So what we want to do over here is that we want to compare noise compounding in circuits which implement Naimark dilation method, which implement some target POVM using either Naimark dilation method or our scheme. So which performs better? So for that, we choose target POVM to be Haar random. Okay, the number of outcomes is D square over here. And the noise model that you see is this depolarizing noise model, where eta is known as the visibility factor. And this visibility factor eta, it will depend on the gate complexity of the circuit which is implementing the scheme, that is standard Naimark method scheme or our scheme. I would also like to mention that this noise model is the same noise model that was used in Google's demonstration for quantum advantage. Okay, so this is typically the noise model that is used for random circuits. So let's start with the standard Naimark method scheme. So this circuit is the circuit that will implement this Haar random POVM, but using the standard Naimark method. Let's say that your principal system on which you want to perform this Haar random measurement is that of an n-qubit system. So as I mentioned very early on, the ancillary system also needs to be that of n-qubit system. Okay, so you have totally 2 n-qubits, and the gate complexity hence scales as this. Correspondingly, the visibility factor eta that you see over here, this decreases in this fashion over here. Okay, now let's come to our scheme. So this circuit will schematically depict the implementation of Haar random POVMs using our scheme. You have n qubits principal system, but only 1 qubit in your ancillary system. Hence, the gate complexity scales like this, and the visibility factor decreases slower than for the standard Naimark method. So you see that our scheme performs better, is more robust with respect to this noise model for Haar random POVMs. Okay. Now let me come to the summary. So a general POVM of, to implement a general POVM on n qubits, you require n ancillary qubits. Now this has implementation issues, which I mentioned early on. So what we do in this work is we propose a scheme to implement such a general POVM using only classical resources and a single ancillary qubit using post-selection. So this scheme is probabilistic, and it will implement your target POVM with some success probability. We have pretty strong evidence to show that to believe that the success probability is actually constant for all POVMs in all dimensions. Okay. Now, what is this evidence? To remind you, then the numerics for SIC-POVMs and Haar random POVMs tells us that this Q success is greater than or equal to 25%. But for non-symmetric IC-POVMs, it tells you that it's around about 19%. Okay. The analytic results for Haar random POVMs tells us that this Q success with overwhelming probability will be greater than 6.5%. Based on this, we conjecture the same, that Q success is above a constant for all POVMs in all dimensions. And we also then finally compare the noise compounding in circuits which implement our scheme versus Naimark's dilation method, and we find that our scheme performs better. Finally, I come to the scope of our results. Now, scope for experiment is that you only need a single ancillary qubit to perform your target POVM, and the success probability is pretty high. So you don't, so your resources don't keep scaling as the dimension increases when you want to implement your POVM, right? Now, what is the scope for theory? Well, as I mentioned earlier, this has connections to resource theory of measurements. For instance, the notion of simulating POVMs using restricted classes of other POVMs, or we believe that Q success, we know that Q success is actually related to other properties of POVMs, for instance, visibility. But what about other properties like the entanglement cost of measurements, so on and so forth? Also, for those people who are interested in non-locality, well, there are relations to the randomness extraction and local hidden variable models. And finally, we believe that our scheme would be useful to study simulation of random circuits with other circuits. So with this, I would like to conclude, and thank you very much for your attention.
Thank you very much for the nice talk, Tanmay and Filip. So there is a pretty lively discussion on Slack, but I think Michał is doing a very good job and taking all the questions away, right. Meaning answering them. So maybe let me just ask one kind of a higher level question. I mean, I understand that you don't fully understand your how good this Q success probability is, but can you say a few words about like a known upper bounds, so that we could judge how close your algorithm, your protocol is to optimal?
Right. Yeah, okay.
So I don't think that we have an upper bound as such for this Q success. I mean, it's a non-trivial upper bound that way, like, you know, that you will always find that the Q success is going to be, yeah. So I don't think that
Yeah, I can like just agree with Tanmay. We don't we don't currently have any like upper bound, and what we can do is of course to check out numerically what's going on, but there is, well, I mean, it quickly becomes super complicated to go through all the partitions, so it's literally impossible to brute force this. Yeah, but I can just comment that like numerically we observe, as I told you, I tested here, I presented here a choice of the best partition out of the very few of them, and we observe like even for those non-Haar random POVMs a high concentration of this success probability, like that the partition doesn't matter that much often. Like you choose a random partition and it's pretty good. Like so that's the empirical observation. Yeah.
But is it clear that this partition structure, that this is how such a protocol should go? Couldn't there be some completely different protocol that magically does better than yours?
I mean, there could be. I mean, there is. I mean, a completely different protocol, unrelated. I mean, could perhaps not even use post-selection. I mean, yeah. So that could very well be the case. It depends on what, it depends on what merit you're choosing. I mean, the point is, like, for instance, like Naimarks dilation method. You know, the success probably for that is 1. So that obviously does better. Of course, there are other issues over there, like, you know, your resource being consumed away. So it depends on the figure of merit, I think.
Right.
Like what do you want to optimize versus what, Asa?
So it seems like there are still a lot of questions to be answered. So I encourage everyone to go over to the round tables. So please remember that the round tables are different for different talks. So there are 3 different round tables for this session. Thank you very much to all the speakers for all the great talks, and see you at the round tables.